Okay, so we'll go ahead and get started. This is a little bit of a kind of a playful session. This isn't a very hard business enterprise-y use case, right? Interstellar navigation, but it really highlights the variety of problem sets that you can apply graphs and network analysis to. So before I go into it, I'm going to just kind of mention a few things as kind of a backdrop. So first, I'm going to talk a little bit about history of computing, where we've come from, and how I think it's really catapulted us into this graph kind of world that we live in. And then I'm going to showcase a variety of graphs. Up there I mentioned there's a little blog that I run, and I do graph or network analysis and visualizations every once in a while. And I'll go through those real quick just to show the variety that you can apply a graph, a tool set, and techniques to. And then what led me specifically to this use case of doing this with stars. All right, so this guy is the man. His name's Warren Weaver. He wrote an essay in 1948 called Science and Complexity. It's a really good essay if you haven't read it before. I encourage you to go to look that up. He breaks science into three kind of periods or three epochs. And he calls the first one kind of dealing with the problem of simplicity. And for those of you who've take any kind of a physics course, right, you have Newtonian mechanics, you have this object acting on this object. Well, we know that no system's like that. You have actually this object acting on this object, this one acts on both of them, and you scale that up into millions, billions, and suddenly that kind of model starts to break down. This next period he called the problem, dealing with the problem of disorganized complexity. And this is really when he was mostly, when he wrote this essay, tail end of this period. And it was the problem, disorganized complexity. What that means is basically kind of black box. You're studying a system, but you're studying the system attributes itself, disconnected from the notion of elements acting on each other. Then he predicted, he's kind of projecting a little bit, saying, well, then we're going to have to deal with the problem of organized complexity. And that, he said, was basically many elements operating in a system and understanding the system, accounting for those interactions, the elements. And that, to me, just screams graphs, right? Graphs are, I have this group of social interactions, I have this biomedical use case, or I have these recommendations, and it has attributes in this network, but they're in terms of relationships inside there. What I find most interesting, though, is he specifically cited that this would require, addressing this problem of organized complexity would require computational power far beyond what they had in 1948. And I guarantee you this, what I have in my pocket right here is, and most of you probably have in your pocket, is far more powerful than any conceivable computer that they had at that time. So I think that's really propelled us into this world. I don't think we could do what Neo4j does without the level of computational power that we have. For example, disk drive cost over time. There's that mapped out there. Memory over time, and notice the axis here is logarithmic. Cost of computing and storage. So this memory and storage, they kind of trail each other by about 5 to 10 years. And lo and behold, a lot of these projects have been birthed as a result of our hardware being liberated. So Hadoop and Neo4j, more or less, first release of Hadoop and Neo4j were open source about the same year. And then Spark came along about 6 years later, right? And Spark's all about memory, as soon as that memory price point was right. And then we have transistor cost, internet transit cost, bandwidth. So these are all really culminating into this world of computational power. So switching from that a little bit, I want to talk about and kind of ask you this rhetorical question. Maybe you can think about this in the back of your head. What's your passion, right? Maybe it's the same thing as what you do for your work. That's great. Maybe you have additional passions, pursuits in your own life. And in addition to that, can you find a graph in that passion, right? Do you like music? Is there a graph that you could visualize there? Do you like, I don't know, books? Is there some sort of a way you could come up with a graph use case, proximity of words for particular authors? So to demonstrate that, these are visualizations I did on my blog, All Things Graphed. So on the left there is let's see if I can identify just by looking at the picture, my LinkedIn network. And these are all from posts that I've done. I try to be detailed about how you could do it yourself. So if you read that, you can reproduce a lot of these on your own. And then on the right there is my Facebook network. It's my Twitter network. People that I'm following, and then if they follow each other. And I'm coloring these by doing community analysis. And so in the upper left, you can even see Neo4j there in kind of the pinkish area. And then there's other, lo and behold, there's a bunch of astronomy ones. There's NASA and JPL and things like that. So obviously, that's an interest of mine. Another one, this one is a network of interactions of proteins in budding yeast. So there's an open data set you can download, and you could start playing with that. Another interesting thing is, well, what is a protein? Well, it's a molecule, right? And what's a molecule? Well, it's a graph, right? Atoms connected to other atoms, right? And those connections have different attributes. So, you scale way down, and it's graphs. And the rest of this kind of presentation, we'll talk as we scale up, you can find graphs too. So graphs are everywhere. A few more. This is another open data set. It's a U.S. Airlines connections. And you can actually export this into Google Earth. And once you do that, you can pull out a joystick and you can fly through your graph, which is kind of fun. So there's another view. I'm from the Seattle area, so that's Mount Rainier, if anyone's curious. Right, another one, WordNet is another open data set that's out there. And what I did is I picked antonyms, so words with opposite meaning, and found what's the pathway between them using only synonym links, right? And so that's what that path looks like there. For your information, it was strong and weak were the antonyms, and the pathway, I wrote it down here, is strong, solid, square, lame, feeble, and weak, right? And what's interesting is you get short circuits where you might get a bunch of jumps, and it makes kind of sense how it's slowly changing its meaning. But then you have things like colloquialisms, right? And that short circuits because oftentimes colloquialisms are rooted in sarcasm. And so that'll get you there real quick. Just a couple more. This is a Wikipedia link graph around the Wikipedia page for the human condition. Really interesting there. This is the political blogosphere. So no surprises there, I guess. This is the Neo4j kernel for, I think, 3.1. And so this is a Java call graph. So if you have, what classes are calling what other classes and the interrelationships there. IMDb, Robin Williams sadly passed away, and I went up and said, well, what if I parsed essentially his acting career on IMDb and scraped that? What would that look like? Some interesting insights there. This is the last one. This is Marvel Author Collaboration Network. So you pick a comic book series, and as you go along, anytime a set of authors or letterers or artists work together, you put them on a graph and connect them. Then you move to the next issue, and you get some interesting graphs there. All right, so that's just a kind of a variety, show you background. You can go on my website and look at those. But for this, we're looking at specifically stars. This has been a lifelong passion of mine. I bothered my father with questions like, how big are stars? What's a black hole? What does it look like? What would happen if our sun came a black hole? What happened if two black holes collided? What do you mean there's time dilation? So eventually, I think maybe he just wanted to have me go and try to stop asking him questions. He threw this book at me when I was about 11. And so I read it, and I understood about that much of it, right? But the big takeaway for me that was really kind of life-changing was I realized, hey, we can ask big questions and use tools to get meaningful answers, right? And I think that's what we're doing with graphs, right? We're starting to ask these big questions that we couldn't before because of the limitation of tool set. This is another set of sketches I did when I was a little bit older about, hey, what would possible spaceships look like that could go, go on long distances. And of course, I've infected my children with this love of astronomy. So on the left there, that's you can go on. Does anyone do the NASA alerts about when the space station flies overhead? Right, you can get those little emails. Yeah. And so I do that, and when it aligns with their bedtime, I'll take them to the back porch and look at that. But if you look in the low right-hand corner there, I pulled up the live stream of the space station. So we're looking at it, and it's looking back at us, which is kind of fun. And then on the right there, when the Curiosity lander landed, I found a way to synchronize their solar system simulator up to the mission control feed, and they had a little augmented reality rover down there. So, and then in the middle, my daughter, for Career Day once, dressed up as astronomy, and I said, "Oh, you mean astronomer?" She said, "No, Dad, I'm astronomy." So it's very meta. I don't know if that's what that says about her personality. All right, so with graphs, right, we can ask connected questions, and we can use graphs to get meaningful answers. So obviously, I don't know how well these next set of slides, probably should have tried to make these brighter, getting a lot of light from the outside. But if you can see it, that's basically a constellation, and it has kind of the myths behind these constellations superimposed on the back. So what are these? Well, these are graphs, right? These are nodes connected to other nodes, right? They're very disconnected, and they were usually, even today, I think a lot of times we think of these as being on kind of a dome around us, right, on this kind of surface. Well, yeah, they're graphs, but they're really three-dimensional graphs. And I have a video, and if this isn't displaying very well, I don't know how well this is going to display, but we'll go to the next one here. So I'm selecting a star here that was in a system, and I'll turn back around here, and you can see these edges, if you saw them there, right? Those are the constellations. And when you go way out from our solar system, you can see how these things that we usually think of as flat, right? I draw it on a piece of paper. They are definitely not flat, right? They are in 3 dimensions, okay? So as we kind of go beyond thinking about these things as these little pictures that are on a surface, we start to see things more like this. This is a time-lapse video, not a time-lapse video, but a time-lapse image of a SpaceX launch, right? We're starting to build edges out to things beyond here, right? So we're forging these networks, right? Every launch is an edge, every destination is a node. So that's interesting. What are some big questions that we could ask here? Okay, so maybe one is, how far would we have to be able to travel for our stellar neighborhood to open up, right? So Proxima Centauri is maybe about 4 to 5 light years away, if I remember correctly. So we'd at least have to travel that far, otherwise we couldn't get anywhere. But is that far enough? That's an interesting question. What would the navigational pathways of the stellar travel look like? What does this network even look like when we start to visualize it? So in order to start asking these questions, like anytime you answer big questions, you have to bring some assumptions along. So I'll just kind of underline these real quick. So the first big one is obviously, well, we can't do this, right? We have no way to travel that far. So maybe we just use our imagination a little bit, right? We can invoke Star Trek or, whatever that, Interstellar, right? So you could, wormholes, superluminal travel, long-term hibernation. You could, pick your favorite science fiction. But at least to start to answer that question, we have to assume that we maybe have some capability to do that way down the line. Another assumption is have a requirement to refuel. And I'm assuming, I think this is a reasonable assumption, that you're going to need mass and or energy. I don't know of a way to do something, travel, without using either of those. So I'm assuming that's still going to be a law of the universe. Another one is the greater the distance, the more the fuel, right? No free lunch. So if you wanted to go on a really long hibernation mission to go to a star, I'm assuming that to keep that system sustained requires energy, right? And entropy likes to rear its ugly head, things like that. And then a limiting maximum distance. So I'm not assuming that we could just simply point and go and we're done, right? I'm assuming that because you have a limiting maximum distance, that you're going to have to be a little bit more careful about how you plan routes. Just like when you fill up your car and go for a cross-country drive, you don't just say, well, I'll get on this highway and eventually I'll get off at New York and I'll be done, right? You have to worry about fuel. Okay, so there's this data set out there. It's a Gliese astronomical data set. It has about 2,000 of the closest stars. Unfortunately, it's in this weird kind of spherical coordinates, and it's not just very obviously translatable. But also, fortunately, I have a colleague at the Los Alamos National Laboratory who helped me get the data from this system into a system that I understand a lot better, which is just Cartesian coordinates, right? X, Y, Z, with our us right at the center. And so that helped me kind of get off the ground here. So now we can start asking these questions. So how far would we have to be able to travel for our stellar neighborhood to open up to us? Okay. So how would we do that? Well, first thing you need to do is you need to calculate the distance, right, from us to all the other stars in this data set. Okay. It turns out that is about a range of about 5 light years to about 75 light years. Okay. And then you need to find a max distance that fully connects the stars. Anyone familiar with the concept of a component? What a component is in networks? So, example, on one extreme is you have a graph, and it has no edges, right? So that's not a very interesting graph. And then the other extreme is you have a graph, and every node's perfectly connected, has a path to every other one. That's a fully connected graph. But then you could still have a graph in the spectrum where you can get from one place to the other, but there's not a direct one. You have to bounce around, right? You have to do pathfinding and things like that. So if you have a graph like that, it has a single connected component, okay? And so if you wanted to find how far we'd have to travel to be able to reach all of these stars, you can load that up in a network and figure out if there's one component, okay? And here's the first little data graph here. If we can only travel, if we assume 5 light years, we have about 1,400 kind of isolated pockets in this graph, okay, of which we're one. We can only reach maybe 1 or 2 other of our closest neighbors. So we bump it up to 6. And 6, now we have a lot less. We're getting a lot more connections in this network. And we bump it up to 7, 8, 9. And we reach this kind of elbow here at 9, 10, 11, and moving on. Eventually you get, if you do 14, then you get a fully connected, you would get a graph with a single connected component. So what that tells us is, okay, if we really want to travel everywhere in our immediate stellar neighborhood, we need, I don't know, it looks like the range of 9 to 14, somewhere around there, seems to do the trick. One thing to note is, and you'll see this later, this network is basically a sphere, and with lots of interesting, kind of interfilamental structures in there. But on the outside, it just, right, this stops. That doesn't mean there's nothing beyond that sphere. It's just that's how far the data set went, right? So my hunch tells me, and when I was playing around with the data on this, it seems like 14 would be a high end on that, right? Where you could probably get to one of the stars that's right out there on the edge if you had more stars around that area that you could jump around to. So, but regardless, 9 to 14 seems to kind of narrow this down. We're starting to get a little bit of a sharpness to the answer of our question. So inverse to that is if you ask the question, well, how many stars are reachable depending on how far we can travel? Right, and that should make somewhat sense, right? The further you can travel, the more connected you are, and the further you can travel, the more stars you could reach, right? But what's really fascinating about this is the flat line there, right? So turns out there's this really sharp kind of threshold where if you can travel anywhere from 5, 6, 7 light years, we're pretty much stuck in our own little pocket, and we can't get much elsewhere. But as soon as you pass that threshold, about 8 light years, 9 light years, and so on, it just hockey sticks right up, and now you're in a much more accessible neighborhood. Okay, so how far would we have to be able to travel? Well, it seems like a reasonable answer might be 12 light years, plus or minus a couple light years, okay? So that's cool, right? We just used networks and network analysis to answer a question that you might have thought, well, that's an interesting hypothetical, rhetorical question. We'll never answer that, right? So that starts to really show the power of networks and graphs. And hopefully the takeaway from this isn't, wow, we can study stars, right? To me, that's really interesting. But hopefully that can get you thinking. Remember that question I asked, what are your passions, whether at work or personally, and how can you ask those big questions? What are the big questions around that passion? And could you use, if you can model it in a graph or a network, can you start to answer things in this way? All right, let's move on to another one. What would the navigational pathways of that travel look like, right? So we've been showing little, bar graphs and things like that, or, line graphs. That's not a network. What is a network? Okay, so here's the first kind of visualization of what this data set actually looks like. And maybe it looks a little bit better over here, less light. So we're right there in the center. Again, this data set is heliocentric, right? We're at 0.000. But this is kind of two-dimensional, so eventually we'll want to look at this 3D. But you can see a little bit of structure here, right? There's kind of a filamental arc over here and so forth. What that really starts to get me to thinking about is, what are the hubs, right? Remember this? I kind of breezed by it real quick, but this is the airline connection graph, right? So are there hubs in here? That's an interesting question. It's a big question. So how can we go about answering that? So who here's heard of betweenness centrality scoring? Have you heard about that? Okay. So if you have a network, obviously there's pathways, right? And particularly if you have a network with a single component, then you have a pathway from any one node to any other node, right? Might be a lot of hops, might just be one hop, but there's a pathway. You can get there. And so what betweenness centrality does is it calculates every possible path. This is kind of the brute force way. There's more efficient ways, more nuanced ways of doing it. But the intuitive way of thinking about it is you calculate every possible path, and each time you calculate that path, you increment a counter on that node, right? And eventually, as you go through and do that, think back of that blogosphere, right, where you had a big grouping here, not too much in the middle. Whatever those nodes are in the middle will tend to have higher scores if everyone goes through them, right? Because they're on a good majority of the pathways. So when we do that with this data set, that gives us kind of an intuition of what are these hubs. So that's what this looks like here. So I'm sizing these nodes here based on their score, their centrality score. And a couple things to notice here. One is I added some color. I'm using the Harvard spectral classification, kind of a simplified version of it, based mainly just on the temperature of these stars. But also, we're right in that center, kind of right dead center in the screen, that bluish, whitish dot. We're not the smallest one on there, but we are definitely not the largest. So why stellar hubs? Why is this an interesting question or an important question? Well, if we were to identify common traveling routes, we probably want to set up waypoints or stations there, right? So that's intuitive, I think, right? In the history of mankind, where has civilization blossomed, right? Trade routes, right? Where are people traveling? And where they travel, that's where you get major cities and civilization, things like that. So if I put my SETI hat on a little bit, well, what if there are stellar-faring civilizations already out there, right? Perhaps hubs like this might be an interesting place to look at. So you heard that news of that star that's mature and has an odd amount of debris in it, right? It could be anything, we don't know, but we're looking, and could this inform that search? Okay. So what are these hubs? Like I mentioned, interestingly, it's not our star. This was one of the most counterintuitive things when I did this. Was I figured it's a heliocentric data set. We're right in the center. We know more about things that are closer to us than we are further away. Of course, we would be really high on the score. No, we're number 49. So that was an interesting thing to learn. But I'll throw a few of these up here, and these designators probably don't mean anything. They don't mean much to me other than I know GL stands for Gliese. So they're out there, right? It's a double. One of them is a double star system. May or may not be visible to the naked eye. So there's lots of variety out there. And so that's just the top 5 there. All right, so let's get to another question. What would the navigational pathways of stellar travel look like? Okay, so remember this is a, right? Remember this is a 3-dimensional graph. So far we've been looking at it in 2D, right? Which I think hides a lot of the topology, hides a lot of the features when we smash it down in just a flat surface on the screen here. So there's a tool out there, just out of curiosity, who's heard of this tool before, Navigator? I kind of stumbled upon it. So if you're like me, you spend maybe a day or two Googling in the background, how do I visualize a network in 3D? And eventually you stumble upon this University of Toronto link, and it's a tool that'll do that. There's a little trick to it, and I confirmed that this is actually how it behaves with one of the maintainers over there. When you load it up, it initially will run a kind of a force separation layout algorithm, and so it'll destroy your 3D coordinates. But you can go into the settings and tell it on load, don't do that, right? Don't apply a visualization layout. And its default behavior is to fall back on any existing XYZ positions that your data came in with, which is exactly what I wanted. So that allowed me to visualize these in 3D. So what I'll do is I'll show you what these networks look like in 3D in a kind of a spinning, rotating movie at different max light year settings. So the first one I'm going to do is 7 light years. And so there we go. So there's our sun. We're right there in the center. And all these, I kind of box the sun in here in red. And then you can see, right, remember that hockey stick in those graphs? 7 light years, we really can just go around the cul-de-sac and back, right? We're not going very far. And some of these stars, like one of them is, I think, Proxima Centauri, another one's Alpha Centauri. Those, I think, are kind of down below because, right, there's a binary system there. So, okay, 7 light years. Yeah, maybe we can go on a little tour, but we're not going very far. So what does 8 light years look like? Let's up that max distance a little bit. So here's 8 light years. So that's interesting. It's getting a little bit more features to it. Maybe we can start to see some hubs, right? And by the way, that question of what hubs are there, that's really dependent on what's your maximum distance, right? If you can travel thousands of light years, then you don't need to stop in, these are the intermediate places. But if you assume a certain max distance, then this is what your navigational pathways look like in 3D. Okay, so let's bump it up even more. What does a 9 light year network look like? Did that switch? Yes. So it's starting to look a little bit more like a hairball. A little bit more features. We're starting to see a little bit of kind of interfilamental structure. Okay. Let's go up to 12 light years. See if I have to tap it again. There we go. All right. So now we're pretty close to being completely connected. When it rotates around here, you'll see that there's one, right at the upper right-hand corner there. There's the star kind of floating down on its own. It couldn't quite reach it with 12 light year max distance. Okay. So another view. This is outside in. I wanted to do another view of what does it look like inside, close to our sun, looking out as things are spinning around you. Now, of course, right, these nodes are way overblown, right? These would be, you couldn't even see them if the size of these stars were actually to scale. But if we zoom in and then have it rotate around us, that's what this looks like, right? So these are these pathways that are just surrounding us. So remember before I started constellations, right? Before you'd look at, people look at the stars and they'd see, things about harvest or their myths and things like that. What would it look like if we looked up and we saw pathways, right, like this, navigational pathways? All right. see. I'm doing all right on time. All right, so that's just visualizing it, getting an idea of what the topology looks like. I personally thought it was the first time I got one of those 3D spinner, visualizations working. I was, wow, that's cool. I didn't think I would get that far. So it's a really cool tool, Navigator, if you want to look at your graphs in 3D. And by the way, I don't mention it. I don't think. Well, no, I do a little bit here. So I did use Michael Hunger's Neo4j shell tools to do this kind of import. So I used, for a lot of the centrality scoring, things like that, I used a tool called Gephi. And it's a way that you can load up a graph and do some more complex kind of network-wide analysis. The limitation there, of course, is it can't scale anywhere near the capabilities of loading a graph in Neo4j. And so it's really cool to see some of the work people are doing. I think they mentioned at this conference that integrating with Spark, or people that are creating platforms where you can run these kinds of iterative machine learning analysis on an actual Neo4j database. You don't have to dump it out and then import it in. And so the format, Michael Hunger's Neo4j shell tools adds a import. Remember, there's an import CSV command. There's also, I believe it adds a import GraphML. So you can load in that format, which is a common graph format in XML. So once you have that loaded into Neo4j, then you can programmatically do things like use Neo4j's Dijkstra's algorithm. And that will give you your shortest path. So then we can start answering really interesting questions. What would it take for me to go from here to there, or from there to here, right? And you can start seeing what these pathways are. So I'll throw a little bit of code up here. This is a chunk of what I ended up writing to do this. So there's a few parameters you got to figure out and to describe how you want them to traverse your network. So for example, one way to do Dijkstra's algorithm is just simply, I care about the number of hops. That's all I care about, right? And that might make sense for certain use cases, right? How many degrees separated am I from this person on this career website? For this, that's not what I want, right? Because no two edges are the same, right? They're all based on distance. And so I needed to do one where it was considering a weight on the edge. And so you describe, okay, well, what is the weight? Well, it's a double, and it uses this property on the edge. So that way it can figure out how to tally it up. And they even have ways that if you wanted to, I'm using their out-of-the-box double comparator and double adder, but you can put in your own implementations there if you had some business logic for how you're adding things up in Dijkstra's algorithm. All right, so Vega is a star that a lot of people have heard about. So my code basically kicks out a JSON document with an attribute called directions. So think of it as almost like an interstellar GPS, right? And so it starts from the sun, right? You can see there it is, XYZ coordinates 0, 0, 0. And then it tells you, all right, what's the next one? Well, you got to travel 5.9 light years, and then you're going to go to GL 699. It's at this coordinate. And then you're going to travel 9.4, and then it's at this coordinate, and so forth. And then at the end, I kind of put the number of hops it takes to get to Vega, assuming 12 light year max distance is 5. And total distance is 37 light years, which is just kind of sanity check, right? You would expect that to be greater than the straight shot distance to Vega, which is the 25 light years, right? If you have to hop to these things, you're going to be meandering a little bit. So another interesting thing to look at here is travel distance and hops for different max distances to Vega. And so at 8 light years, your travel distance jumps up to about 55. Max distance of 8 light years that you can travel. You're going to have to make 9 hops, and it's going to kind of kill your distance there. And then if you move up to 9 light years, then you're going to have to make less hops, 6 hops, and so you'll save a little bit of distance there. But then there's this range keeps coming up in this data set, right? 12 plus or minus 2, right? And so it flatlines, where it doesn't matter if you can travel 10, 11, 12, 13, or 14 light years, you're making the same pathway. I didn't go so far. So what it would look like is you come down here, flat line, and then it's going to taper off eventually until you have one hop, right? And the distance would be exactly the straight shot. And so it probably is going to look like this flat line. But I found it fascinating that you see this range, right? That 12 light years plus or minus. All right, so I'll throw up a few of these. So I found a few stars that have some attributes that are notable, and then said, well, what would a pathway look like? So this first one is known as 51 Pegasi, or Pegasi, if I'm pronouncing that right. But it's the star with, kind of trivia here, that the first exoplanet ever confirmed. Okay? And so it kind of has a killer pathway there. So you're jumping around all these different stars and a total distance of 82, almost 83 light years, 11 hops. Right? So that's what Dijkstra's algorithm in Neo4j kicked out, doing that. Another one is GL667, which at the time when I did this, it had a confirmed exoplanet with the highest Earth similarity index on it. Since then, it's now been bumped down to 2. There's another confirmed exoplanet that has a higher Earth similarity index. A feature that's notable on this one is it's a triple star system. So what would that be like to be a potentially habitable planet with 3 stars? And it's only about 3 hops to get to that one, once you have that network figured out. Another one here is, let's see what was notable. Oh, this one is really fascinating. This star is hurtling towards us right now. And about 1.4 million years is going to come within 1 light year of us. And a lot of scientists think that that will disrupt the Oort cloud around our star and greatly increase possible impacts. So maybe it's something we don't have to worry about in our lifespan, but definitely much shorter than, you know, our star exploding or something like that, right? So there are, this is another little tidbit. So maybe kind of, I don't know how in the world you would do this, but if you wanted to get out there somehow and try to push it just a little bit, I don't know how you would do that. But maybe there's enough of a course correction there that you could avoid something. I don't know. We're already hand-waving about traveling this far anyways, right? What's a little bit more hand-waving? Another one, this is Vega, so this is the pathway that we looked at before. So, and these are all assuming a max travel distance of 12 light years. And so load that up, run that algorithm in Neo4j, and it kicks out this pathway. 5 hops, total distance of 37 light years. One more here, only have a few minutes left. This is Arcturus. It's the 4th brightest star in the night sky. Because of that, it has a really long cultural history with, you know, mankind attributing all sorts of things to it, which makes sense. I mean, you're trying to figure out any kind of normalcy or predictions around you. You're going to look at something that's predictable, like the position of a star in the sky, especially when it's really bright. So it also has 5 hops, and I think it weighs in 42 light years, so a little bit more than the pathway to Vega. All right, so what's next? So I would love to run this on a newer, larger data set. Another thought I also had is maybe there's a galactic analysis here. Take it to that next Kardashev level, right? So I didn't account for star movement. So if it takes you any amount of significant time to travel between these, you're going to have to account for that. Although if, for whatever reason, your Star Trek-style mode of transportation takes you there pretty quickly, maybe it's negligible. But you'd have to at least update every once in a while. So more practically, we're down to Earth here, but looking up, is there a possible value for analysis in SETI, right? It's a big task trying to figure out which stars, and they have, I'm sure, lots of analysis. I'm curious if this particular analysis has been done to try to find hubs, right? Those travel hubs. I don't know anyone at SETI, but who knows? Maybe there's a possibility there. And then Asteroid mining. So maybe there's, if you were to send out, I mean, there's planetary resources. There are companies that have 30-year, X number of year roadmaps of getting things out there and mining asteroids in our solar system. So if you were, again, if you had to travel between these things, maybe there are hubs where you'd want to set up waypoints or facilities, pipelining strategies, things like that. So that's another more use case kind of down to earth here. So that's it. So kind of fun, different use case, and hopefully that was enjoyable. Thanks. Yeah, we have just a little bit of time for 1 or 2 questions is all. Yeah, in the back. The question was, do I have a departure date for Vega? No. It is Back to the Future Day today, though, so anything can happen, right? Any other questions? Up front.
What would be your prediction for 2045?
What's my prediction for 2045? I have no idea. Although one fascinating thing to think about I'll mention is if you follow the size and compute power of our computers, who knows if it'll keep going down Moore's law and the size and the price point and the computation power. But you could have something as powerful as this, the size of a human cell. What was that? Where do I see myself in?
Yes,
in 2045. In 2045? I have no idea. Maybe retired. That would be nice. Okay? Yeah, one more. It's outside this data set. So now I watch the news, and whenever they mention something, I look and say, is it my data set? Yes, I can see the pathway, and I've done that. But then a lot of times they're so far out that that's why I mentioned I need a bigger data set I can run this analysis on. Yep.
Have you seen the Hipparchus data set? I
Um,
think it's Hipparchus. There's a project that mapped the 3-dimensional coordinates using different positions of the probe at different times of the year, so they could get like parallax.
Oh, cool.
Distances.
I don't know. I haven't seen that one.
It's like 20,000 stars or something.
Yeah, that might be a good one to start at. Okay. All right, thank you.